Year 12 and welcome to Purple Mountain Education. Today we're doing the 2025 HSC paper for Maths Extension 1. This is part 4, question 13, worth 16 marks. Question 13a, it is given that dy dx equals 5 on y and y equals minus 4 when x equals 0. Find y as a function of x. Pause here to try yourself. Okay, so the fact that dy dx equals 5 on y means I can separate that. Y dy must equal 5 dx, and I can integrate both sides. I'll get a half y squared equals 5x plus c. Now I know that at x equals 0, y equals minus 4, so let me sub that in. A half of minus 4 squared equals 5 times 0 plus c. A half of 16 is 8, so that's implying that c equals 8. So my equation is now a half y squared equals 5x plus 8, or y squared equals 10x plus 16. Now I need to take the square root, and I need to be thoughtful about whether I'm going to take the positive or negative square root. The fact that at x equals 0, y equals minus 4 tells me I need to take the negative square root. So y equals negative root 10x plus 16, and that's my answer. Question 13b. 8 guests are to be seated at a round table. If 2 of these guests refuse to sit next to each other, how many seating arrangements are possible? Pause here to try yourself. Okay, so I know with n guests seated in a circle, the answer without restrictions is n minus 1 factorial. So with no restrictions, it would be 7 factorial. If 2 people were sat together, I could do that in 6 factorial times 2 factorial, many ways. And so the answer they're looking for is just the difference between those two cases, 7 factorial less 6 factorial 2 factorial. Reach for my calculator to get these numbers. The answer is 3,600. Question 13c. At time t, a particle has position vector as shown, velocity vector v, and acceleration vector a. Find the time when the angle between v and a is pi on 4. Pause here to try it yourself. All right, so given that r of t equals ti plus 1/9 of t squared j, I'm going to differentiate once to get the velocity vector. So that's 1 plus 2/9 t j. I'm going to differentiate again to get the acceleration vector. Note that they're vectors. So I'm not going to get any I, I'm going to get 2/9 for j. All right, I'm interested in that angle, so I'm encouraged to think about the dot product between v and a. So in general, vt dot product with a of t is going to be the size of v times the size of a times cos of the difference between them, which I know to be pi on 4. So let's create that dot product. It's 1 times 0 plus 2/9 of 2/9. There's a t there. And that is the size of v is 1 plus 2t on 9 squared. And the size of a is 0 squared plus 2 on 9 squared. And cos pi on 4 I can evaluate to be 1 on root 2. So let's just tidy this up a little bit. The left-hand side is 4t on 81, and that equals the square root of 1 plus 4t squared on 81 times this, which is 2/9, and this is times 1 on root 2. So pulling that out the front, I've got 2 on 9 root 2 times this square root. I can take the square root of both sides. Rather, I can square both sides, but first of all, I'm going to tidy up the left-hand side. So let me send this 9 root 2 over here times 4t all on 81 times 2 equals this term over here. Okay, so just tidying up that left-hand side, I've got 2 root 2 t on 9 equals 1 plus 4t squared on 81. Now I'm ready to square both sides. So the right-hand side just turns into 1 plus 4t squared on 81. 2 root 2 I recognise as root 8, so when I square it, I'll just get 8t squared on 81. So if 1 plus 4t squared on 81 equals 8t squared on 81, it must be the case that 4t squared on 81 equals 1, or t squared equals 81 on 4. When I take the square root of that, t is plus or minus 9 on 2, but we know t is positive by the context, so t equals 9 on 2, and that's my answer. Question 13D. A bag contains counters, some of which are green. 100 trials of an experiment are run. In each trial, one counter is selected from the bag at random and its colour noted. The counter is returned to the bag after each trial. Let x be the random variable representing the number of times that a green counter is selected. Given that the expected value of x is 20, and the probability that x is greater than or equal to k equals 0.0668, find the value of k. You may use the standard normal approximation of the information on page 13. Pause here to try yourself. All right, so we know that x is distributed as a binomial as so on, where n is 100, because we're told n is 100. Straight off the reference sheet, we can also use the fact that the expected value of x equals n times p. We know at n equals 100, the expected value of x equals 20. So 20 equals 100 times p, so p equals 1/5. That also tells us that 1 minus p equals 4/5. Okay, again, straight off the reference sheet, the variance is going to be given by np1 minus p, which is 100 times 1/5 times 4/5. So we've got 4/25 of 100, that's 16. Now the standard deviation is going to be the square root of the variance, so we're going to get the standard deviation being 4. All right, so now we know that x is distributed normally with expected value of 20 and our variance is 16. From that information, we're considering when is it true that x bigger than or equal to k equals 0.0668. So we need to find the z value that corresponds to that. So z by definition is the score minus the mean over the standard deviation. So we're interested in finding the z score such that we're at k minus 20 all over 4, and that equals 0.0668. Now, when I glance at the table of values that they pointed me to on page 13, let's just have a little look at them. I noticed that it's actually given to me as the probability that a random variable will be less than or equal to some z score, not more than or equal to some z score. So instead of investigating 0.0668, I need to consider 1 minus 0.0668, and that number is 0.9332. That's the number I'm looking for on my table so I can figure out the z score. And it is here. 0.9332 occurs at a z score of 1.5 straight off the table. Okay, so let me use that in my working now. I know that I'm actually interested in being less than or equal to k minus 20 on 4 equals 0.9332, and the table tells me that this is a z score of 1.5. Okay, so now I simply need to consider that. K minus 20 on 4 equals 1.5. K minus 20 is 4 times 1.5. I get K equals 26, and that's my answer. Question 13e. The Pascal's triangle relation can be expressed as this. Show that relationship, hence or otherwise prove this. Okay, pause here to try yourself. All right, so notice that in part 1 we're given a relationship and we're told do not prove this. So I'm allowed to use this. I'll call this equation 1, but I'm not obliged to prove it. So let's notice the structure of equation 1. It's involving n and the previous number, n minus 1. It's involving r and the previous number, r minus 1. Let's look at what we're obliged to show and notice that it's involving m and the next number up, m plus 1, and r and the next number up, r plus 1. So let's rewrite equation 1 where instead of n, I'm going to write m plus 1, and instead of little r, I'm going to write capital R plus 1. So the left-hand side is m plus 1, capital R plus 1, and then mr plus mr plus 1. All right, I'm getting close, but I'm not there yet. I really just want mr as the subject of the formula. So m choose r, making him the subject of the formula. It's m plus 1 choose r plus 1 less m choose r plus 1. And that's exactly as I was required to do, as required. Okay, let's focus on part 2. Hence or otherwise prove this relationship. All right, so I'm certainly going to be relying on the hence. It's going to be useful to use the relationship I worked out before. Okay, so let me just remind myself what I need to prove. I need to prove 2000 plus C 2001 choose 2000 2002, choose 2000, all the way up to 2050, choose 2000 equals 2051, choose 2001. All right, let's take that left-hand side and rewrite it in a different order. So the left-hand side equals 2050, choose 2000, plus the next term would be 2049, 2000, plus 2048, 2000, and so on, all the way down to 2001, choose 2000, plus 2000, choose 2000. All right, now I'm going to use the relationship I had before. Let me take this first term and rewrite it using the relationship above. So I can rewrite this as 2051, 2001, less 2050, choose 2001, and then the next term, this one, turns into 2050, 2001, less 2049, 2001, and so on, all the way down 2001, 2001 plus 2000, 2000. All right. So what I'm noticing is the first term will persist, but the pairs of terms following are minus this plus that, minus this plus that. So they're going to cancel. So I'm going to be left with, this one will end up being a minus, it's half. I'm going to have minus this one. I'm going to have plus the last one. And those final two terms are just minus 1 plus 1, so they'll go away. Those, and I'll just be left with 2051, 2001, which is the right-hand side as required.